Hi! In this video, we extend the definition of limit from sequences of real numbers to functions of real variable. The underlying idea is the same. We want to determine what happens to the quantity f of x as x approaches a certain limit point x star. This limit point can be plus infinity, as for sequences, or minus infinity, or any other point in the real line. However, as soon as we think about how to define this operation, we realize that this operation is not necessarily always defined. In fact, to discuss the behavior of the quantity f of x when x approaches the point x star, we need that f be defined for x near the point x star. For example, it doesn't make sense to ask what happens to log of x as x goes to minus 1, because there is no log of x when x is close to minus 1. So we understand that the points x star at which the limit makes sense must fulfill some condition. In particular, they must be surrounded somehow by points of the domain. This leads to the definition of accumulation point. Let D be a set of real numbers, and an x star, either finite number or plus minus infinity, is an accumulation point for D if there exists a sequence of points of D different from the point x star that goes to that point x star. So the idea is that since this sequence is different from x star, these points should be accumulating on the point x star, and that's why we call this an accumulation point. So let's see some examples of this definition. Here we have the set D of naturals, and we show that plus infinity is an accumulation point. We just need to take the sequence of natural numbers, which is contained in the set. It is different from plus infinity, and it goes to plus infinity. If the set is the set of integers, in addition to plus infinity, we can show that also minus infinity is an accumulation point. In this case, it is sufficient to consider also the sequence of the opposite of natural numbers, and they go to minus infinity. In this third example, we have the set of strictly positive real numbers, and we show that 0 is an accumulation point. We just take the sequence of fractions 1 over n. They are positive, they are different from 0, they go to 0. Great! We are now ready for the definition of limit. So let f be a function defined on some domain D of the real line, and x star be an accumulation point for the domain D. We say that the limit of the function f of x as x goes to x star is equal to L, finite or infinite, if the following holds. If for every sequence taken in the domain D different from the limit point x star, such that xn goes to x star, then f on that sequence goes always to L. Here you can see these dynamics on a figure. You see the points x moving in the domain and the values of the function going to the limit. We may summarize this definition with the famous saying that all roads lead to Rome. Now, an important feature of this definition is that the point x star, where you compute the limit, is not involved in the definition. So you don't see the value of f at that point. This is because of two important reasons. The first one is that in most of the limits, the function is not defined at the point where the limit is computed. So you use limit exactly because you want to determine what happens where the function loses its meaning. And second, we can have cases where the function is defined at that point where you compute the limit, but the value of the function has nothing to do with the limit. So take this function, which is always equal to 0, except at one single point, the point x equals 0, where the function is set equal to 1. Now, what should be a reasonable limit for x going to 0 of the function? Well, we may think that when x goes to 0, the value of x is always equal to 0. So the limit of the values will be 0 reasonably. And this is exactly what happens if we take our definition. So I suggest you to verify this by using the definition. However, if we would remove the restriction that the sequence xn that goes to the limit point must be different from the limit point, so we allow the sequence to touch the limit point, here we would see that if we take a sequence that goes to 0, but different from 0, the function would go to 0. But if we take a sequence constantly equal to 0, that goes to 0, the function would go to 1. So it wouldn't be true that all the ways lead to Rome, in other words. Now, let's see what happens on some concrete examples. Here we have this limit for x going to 0 of 1 over x squared. It is clear that the function 1 over x squared is defined for x different from 0. Now, to verify this according to the definition, we have to see what happens when we take a generic sequence of points xn in the domain D, which is, by the way, in this case, the real line except 0, different from 0. They are automatically different from 0 if we take in the domain D, and such that they go to 0. Now, in this case, the value of the function would be 1 over xn squared. And clearly now this denominator goes to 0. And since they are positive numbers, because they are squares, it goes to 0 plus. We know that 1 over 0 plus is not an indeterminate form. We have a rule to compute this limit, and the limit is plus infinity. This is the outcome, whatever is the sequence xn. So we can conclude that according to the definition we gave, the limit of this function is exactly equal to plus infinity. Here we have the limit for x going to 0 of 1 over x. That looks similar to the first example we have seen. But here we could notice the following fact, that if I go to 0 from the right in this way, the quantity 1 over x should go to infinity with the positive sign because x is positive, while if I go to 0 from this side, the quantity 1 over x should go to minus infinity. In fact, I have that here. If I pick the sequence xn equal 1 over n, and I evaluate the function f on this point xn, this is, by the way, a sequence contained in the domain, which is everything except 0. So we are in the domain, it goes to 0. But f of xn is equal to n, that goes to plus infinity. While if I take a second sequence yn equal minus 1 over n, this now makes fn, f of yn goes to minus infinity. So as you can see, I got two opposite limits here. Particular, it is not true that all the roads lead to Rome, because there are two different roads that lead to two different towns. So in this way, I would conclude that this definition is not working, and therefore the limit does not exist. Now, this example shows that if we find two sequences in the domain xn, yn, different from point x star, such that both goes to x star, and along which the function f has two different limits, L1 and L2, then the limit cannot exist. Great. What can you do now? Well, first I would suggest you to practice with the definition, which is the best way to master it. You could calculate, for example, these limits that you see on the screen. Be careful with the second one, which is likely more complicated. And then perhaps you could challenge yourself with some more difficult problems, like this one shown on the screen. Good luck and have fun.